All right, so I'm going to work through some of the problems off the review for test 2. The answers to the review are posted in Canvas. All right, folks wanted to see questions 12, 13, and 14, so let's look at those. These come from the Chapter 10 material. Number 12 is really a fundamental counting principle problem. On this one, we're trying to come up with possible radio station call letters. It's kind of like password problems. Okay, they're composed of letters. There's 26 letters in the alphabet, so that's important to know. The first letter has to be just a K or a W. So there's only two possibilities for that first spot. And so if I were doing my tree diagram, I would have 2 branches with a K or a W. But then when I go to do my second letter, okay, I notice that repeats are allowed, okay, and there's no other restriction for that spot. So there'd be 26 branches off of each of those letters. Same for the third spot, 26 branches off of each of those branches, because there's no restriction in the third spot, but they can't end in an O, so I don't have 26 letters to choose from. I only could pick from 25 letters. There's only 25 possibilities if I can't be an O. And then I would just multiply that out, and I would get 33,800 as the answer to that one. Number 13 is also a fundamental counting principle problem in a way. There's 6 people who could line up in the first spot, but then one person would be there. So now there's only 5 people left for the second spot, then 4, then 3, then 2, then 1. Okay, that we also found that that's the same as 6 factorial. So you could also do it by just doing 6 factorial, and that should turn out to be 720 ways 6 people can line up for tickets. Okay. Now in question number 14, there's really 3 questions there. The first one is that we're going to pick 5 letters out of the word payment. Okay, we're going to pick 5 letters, and we're going to see how many different arrangements of 5 letters we can make. So if I took 5 letters P-A-Y-M-E versus A-P-Y-M-E, those are different arrangements of letters. Okay, that makes it a P problem. So for that first question, I should take those 7 letters, okay, choose 5 of them, but use the permutation feature on my calculator. That's doing the same thing as me taking 7 possibilities for the first letter, then 6, then 5, then 4, then 3, and I would stop there because I'm only going to be filling in 5 spots, okay, making 5-letter arrangements. That would be the same as doing 7 with the permutation feature followed by a 5. All right, so that would turn out to be 2,520. 2,520. Now, if I still had the word payment, but I was using all the letters, then it would be 7 with the permutation feature 7, which is the same as 7 factorial, okay? And 7 factorial, let's see what that turns out to be. 7 factorial, or 7 with the permutation feature followed by 7, would be 5,040. All right, now when I get to the word milliard, I want to arrange all the letters in this word, and there's 8 letters, so you might think all I got to do is 8 factorial, but there's lookalikes, right? There's I occurs twice and the L occurs twice. So that means I need to divide by the ways you can arrange 2 letters, and I need to do that twice, once for the I and once for the L. So when I do that, I wind up with 10,080. That turns out to be equal to 10,080. So I'm going to go into the left with it since I ran out of room. Okay? All right, now the next group of problems I'm looking at are the problems dealing with odds. Okay, so it's going to take me a minute. You go ahead and get to those as well, because I have to go to a different screen to make another snip. So hold on a second. Go ahead and move to questions 23 through 26 people wanted to see. So I'm going to go ahead and take a picture of 23 through 26, and then we'll handle those questions. Okay. So these questions primarily are dealing with odds, or at least these are. These are odds. Okay. And remember, odds are going to be something to something. Okay. All right. So this question, let me get that to blow up a little bit. Okay. We got a number cube labeled with the numbers 1 through 6. So basically rolling a die. What are the odds against getting a 4? Okay. All right. So odds against getting a 4. So this would be not 4 here to 4. Okay. So odds against getting a 4. So this is number 23. Okay. The chance of not getting a 4 would be 5 possibilities to the 1 chance of getting a 4. So you would say 5 to 1. Okay. All right. So I'm not trying to do a fraction there. Let me erase that so you don't think of it like a fraction. Okay. But 5 would be all the ways of not getting a 4 to all the ways of getting a 4. Okay. So odds against 5 to 1 is what you would do, because there's only one way to get a 4 and there's 5 ways to not get a 4. And odds is 5 to 1. All right, now we got these cards that just have 1 through 5 on them. We want the odds to start with in favor of getting an even number from those cards. So do you see how there's 2 even numbers, right? So there's 2 even to 3 that are not even. So it should be, since we want odds in favor of being even, we should have even first. On the one above it, we did not 4 to being a 4, okay? So one possibility would be a 4, 5 would not be on 23. Here we want the odds in favor of getting an even number, so we'd want even first, not even second. Okay, if we want odds against getting an even number, odds against getting an even number would be 3 to 2. Okay. Both of those were odds. Now, if I want the probability of getting an even number, then it would be 2 divided by 5. Okay. Be 2/5. All right, 25 is an odds one. Okay. So we know that the probability of an earthquake occurring on a particular day in a certain area is 400ths, 0.04. Okay. So you might want to think about that. This is really the same as 400ths. Okay. So that's the probability that it does occur, is 4 out of 100. So that would be the earthquake happening out of the total out of 100 times. You got 4 in 100 times that earthquake would occur. All right, now we want the odds. So that means we want it to be something to something, and we want the odds against the earthquake occurring. So that 4 you could think of as being there, and this would be the 96. So like 0.04 would be the probability the earthquake occurs, then wouldn't 0.96 would be the earthquake not occurring, probability of the earthquake not occurring. Okay. Would be 0.96. Okay. And then if you thought about that, 96 out of 100, you want number of times it not occurring to the number of times it would occur, since it was odds against an earthquake occurring. And then in reality, you should simplify that. So 4 would actually go into 96. And if you did, 4 would go into 96 24 times. So your final answer on that, I would accept if you did the 96 to 4. I would take it, but you really should reduce your ratio by dividing by 4 and getting 24 to 1. Okay. All right, and people also wanted to see number 26, so we'll go ahead and do that now. It's not really an odds question, but 59 out of 100 births turns out to be a baby with brown eyes. So that's just an observation. That's like empirical probability. Says 59 out of 100 births in some country winds up being a baby with brown eyes. So how many brown-eyed babies would you expect if you had 660 births? So for every 100, you expect 59 to have brown eyes. So all you got to do is multiply that by 660, and that turns out to be about 389.4, so about 389 brown-eyed babies you'd expect in 660 births. Okay. All right, the next chunk I'm going to look at are questions 30 to 34, so you be looking at those. I've got to go grab that portion of the review, so it'll just take me a second. You go ahead and look at 30 to 34. Okay. All right, so question number 30 is a probability. We're being asked to get the probability that the size of the family is going to be less than 5. Less than 5 means 4, 3, 2, 1, or none. Okay. We've got these probabilities in this chart given to us that shows the distribution of the family size in a U.S. city. Okay. And so we would not include 5 because it has to be less than 5, but we would add up 2, 3, or 4. Family size of 2, 3, or 4. And if we added that up, that would turn out to be let's see, what does that add up to be? 0.864. And so that would be your answer. Okay. 0.864. So the tricky part there is to be sure not to include 5. You need to be strictly less than 5. All right, so let's move on. 31, you're dealt 2 cards successively. That means one after the other. But what's important is you're replacing the card the first time. Find the probability of getting a heart on the first card and diamond on the second. So it's an and. Okay, so we want the probability of a heart on the first draw and diamond on the second one. So when we think about this, there are 13 hearts and there's 52 cards. 13 out of 52 is the probability of getting a heart on that first card. Now, I'm getting ready to draw my second card. That first card, which was a heart, went back into the deck, so I still have 52. And diamonds, there's 13 diamonds left in the deck. And then I just need to multiply those. So I'll let you do that calculation. Okay, that's going to ultimately, after you get it all fully simplified, number 31 turns out to be just 1/16 when you're completely done. All right, now 32, we're dealing ourselves 2 cards, and it's without replacement of the first one. Probability that both cards are black. Probability we get black the first time and then black the second time. Okay, so there's a 26 out of 52 chance, probability of 26 over 52 of getting black on your first draw, and then that black card is not going back in the deck, so then there's only 25 left out of the 51 cards in the deck. So you would take 26 50 seconds times 25 51st, and get it all good and simplified, and that should turn out to be 25 over 102 once it's fully simplified. Okay. Right now on 33, 2 cards are being drawn without replacement of the first, but here we want the probability on 33, we want probability that the second card is red, and it's a given that the first card was a heart. Okay. So that heart we picked the first time, since that heart's not going back in the deck, it affects how many red cards we have left for our second draw. And this one is like the ones we were doing in class. They really just want to know the probability for that second card. When you go to get that second card and you want it to be red, you have to think about the fact that a heart was selected first. So instead of having 26 red cards left in the deck, you picked a heart the first time. So that means there's only 25 red cards remaining. And you used to have 52, but once you pick that heart, there's only 51 left in the deck. So the answer to 33 is just the probability for that second card being red, but we do assume that the first one was a heart. So instead of 26 red cards, there's only 25, and instead of 52 cards in the deck, there's just 51. Okay. Right now on 34, this one, what they're asking us for is the probability in words, the probability that we get a diamond, right? Because that's B is diamond, given that if A is the event a queen is selected and B is the event a diamond is selected. Okay. B was diamond, given that a queen was selected first. Okay. You know, I'm not going to be able to, that one kind of depends on that one. Let's omit number 34. I have to be careful about how I word those, because it kind of depends. When you select a queen, it kind of depends on whether that queen was a diamond or not. So that one right there I really need to toss out. Just omit that guy. Okay. All right, now the next chunk of problems I want to look at are questions 27 and 35. All right, I'm going to go ahead and do 35 while I have this screen, and then I'll go back and pull up the screen for 27. Both of these have data organized in a contingency table. Okay. All right, so on this one, what I've got here is the smoking habit situation, and all the totals are given there for you. Okay, so those are our totals. Here we're going to be picking just one of the surveys. Find the probability the person chosen is a non-smoker, given that the person was a woman. Okay, non-smoker, given that the person was a woman. So the given that statement, it can be thought of as a way of reducing your sample space from the original 1,079. You're going to really be focused on the fact that you know you're dealing with just the 529 women. So that's going to become your denominator. Okay. Then the numerator is going to wind up being the number of non-smokers. So that would be the 376. And on that one, not sure if that reduces or not, so let me try it. If I do 376 divided by 529, That one doesn't reduce on the calculator, like it doesn't come back. Let me try it using my fraction key this time. Okay, so that would be it as a fraction in simplest form. And this didn't specify whether they wanted a fraction or a decimal here, but it's probably safest to leave it as a fraction. Okay. All right, now I want to back up and look at number 27. Okay, so I'm going to go to a different screen where I had 27 saved. So let's see, I think it was this guy. Yeah. Nope, you can't really see it. All right, I'm going to go ahead and snip that one. You be looking at number 27 while I'm grabbing it. Okay. Okay. And so 27 is also a contingency table. The totals are missing on that, so I'm going to go ahead and put the totals in real quick on both edges. So this is 71, 68, 68, giving us 207. Then across the bottom we have 40, 45, 49, 57, and 56 seniors. Okay. All right, so here we want to know what's the probability that a student prefers cheese toppings. Okay. Well, 71 students prefer cheese toppings out of the 207 students. Okay. All right, now this one is what's the probability that a junior would prefer meat toppings? Okay. All right, so I would probably word this more directly. I'd word that one. This is question 27. All right, on that one, I would word that one more like, what's the probability that that the student prefers meat toppings given that they're a junior? It's the same as that. Same as student prefers the meat toppings given they are a junior. Okay, so I'd word it like that since that's a more clear way of wording it, similar to what we did in class. So what's the probability that a junior would prefer meat toppings means to focus on a junior. Okay. So the denominator for B is going to be 57, and the meat toppings would be 16 out of those 57. And that doesn't simplify. Okay. All right, so that covers all of them. You could omit 34 because there's a little complication there, since if you, on 34, if you select, if you think about the queens, it needs to, I needed to word that backwards. I'm tired right now, so I'm having trouble thinking about it. Oh, no. Let's go ahead and look at 34. I was just tired and I wasn't thinking straight. Let's go ahead and do 34. Don't omit that one. It's not as bad as I thought I had worded that backwards from what I wanted it to be. But really, we're okay. We can do it. So let me finish up by looking at 34. So you don't need to omit that one, because it's really the probability that you get a diamond given we're dealing with queens, given that we know we narrowed it down to queens. So that, I thought I had worded it the other way around, and that would be a problem. If I ask it that way, it's okay. Okay? Because the probability that you're going to get a diamond, assuming you have queens, would just be, there's 4 queens. That's your denominator, right? That's the given that statement. And one of them is a diamond. I was worried that I had it the other way around, and then it would be a much more complicated question. But that one's okay. This is okay. Okay. All right, so there's just a few of them. Watch it if it helps you. Make sure you work the questions from start to finish, from looking at the question and then checking the answer. It's much easier and not good preparation to look at the answer first. Also, don't forget to review your notes and your homework as well.